время, ну, несколько лет, многие люди используют несколько социальных сетей в одно и то же время. Причем они так heavily используют. Speak English, sorry. Yeah, so they use more than one social network at the same time. Because yesterday I had another reported Russian about the same thing. So just I'm sorry. They need to use many social networks at the same time, and they actually do, and they use it very heavily, right? So it can be Facebook and Instagram, because different social networks provide different services and serve our different purposes. So, in fact, there was a research by PAW Research Internet Project Social Media Update 2013, and they say it's around like 57% of people use more than one at the same time. So, and all these sources, they describe our user in a multiple ways, describe from multiple perspectives, right? So Twitter, as we already said, or maybe Facebook, can be described in a textual view, right? In the form of text. Another service like Instagram can describe it in a visual view, while one more, like location-based social network, like Foursquare, can describe it in a location view, right? In a geo view. And it's strange, I think, and we feel it's not reasonable to leverage only on one source. It's very important to combine all the sources together to get the analytics. And as I will tell you tomorrow, we actually found that it makes sense and it's actually improved the performance. So it's very important. That's why in this lecture I will be focusing on image data and in location data. Now currently we are working on sensor data as well, so we actually leverage on some signal processing stuff, see frequency components and so on, based on sensors, the variable sensors. But that research is ongoing, so I guess we can read about it in our cigar paper if they will accept us and everything is fine. And maybe later, or maybe after 1 year, we can talk about that part as well. So here, today, we will focus on images and location. And do we have somebody from image processing background, some image retrieval? Okay. So it's mostly NLP people, right? Okay, so I expect you process text for assignment very well. Then, yeah. Then other stuff, maybe just third observation. So we have our image, right? An image is represented as basically intensities of colors. Many different formats. One can be RGB, everybody knows what is RGB. Another one can be some translational broadcasting formats like our TVs use, like YUV and other standards like PAL, ZCAM and so on. Other standards are used are comfortable for human, or comfortable for people. So it's related to things that we actually see colors not linearly. What do I mean when I say by not linearly? How do you think?
Exponential.
Yeah, it's not exactly exponential, but what I mean by not linearity in like in the fingers, what do you mean by this? The point here is if the number for intensity of RGB picture change, it doesn't mean for us it's also change. In fact, we are much more sensitive to lightness, to brightness of image than for its colorness. So there's a certain way how human eye see the spectrum. It's a very, very short spectrum, all the wavelengths. we see it in a certain way. So actually RGB is not really suitable for human to work with. Just because for us it's not obvious how to set up color we need by just combining these three components. So they come up with some other formats, YCRCB, for example. This one is used in JPEG. Then, you know JPEG, right? It's very standard geometry code. So this one is made by chrominance and luminance. This one more close for human. Another nice point here that this chrominance and luminance components can be treated independently from the first component of the image, lightness. So basically, we can process these three values completely independently, come up with something, and then combine back, and we will not really do something weird. We will not really lose information. Because for RGB, if we process them independently, we may come up with something straight just because it's not linearly changed. And some colors are more important, other colors are not important. So anyway, we have these image representations, and it's usually either grayscale or color scale, and it's a number of values. Like in RGB, it's red, green, and blue, right? So in fact, it's these three components are all come up with these three values. Let's say from 0 to 155 or somehow like this. And we need to extract some features from these images. So just intuitively, what features can we extract out of this image? What we can use?
Edges.
Edges. What is edge? For a plane, for example.
I understand the question. Separation an object from the background or something like that.
By the way, how do you think? Is it easier to detect some?
No.
Maximum difference between adjusted pixels in color.
Yeah, so we talk about
this would be accounted for.
We cannot judge about single pixel, right? We always need to see the neighbors.
Yes.
It's quite important.
But by colors there is but background has a cloud. It's white, and in plane is also white. So they
and also projector is not very good.
And also by that, but computer can't.
No, it's correct. Edges is actually a very powerful feature. I agree with you.
But it's very difficult to correct edges.
Not exactly. There are some methods to extract edges. I will talk roughly about it. But how do you think? What is easier, to detect some complicated objects or detect some simple objects, like plane or apple? What is easier to detect and classify?
Yeah, for person or for computer?
Well, you have two classes, planes and apples. So which one is easier to detect?
It's easier to detect simpler object. And the simplest task is to detect an object which differs from the background. If the object is different to the background on which it is located, it's the easiest task it's the easiest detection task.
It's a psychology point of view, right?
Yeah, psychological point.
For computer vision, how is it?
For computer vision, of course,
Opposite or the same?
It may be different because there is no such mechanism as attention for computers. So the computers analyze the whole picture, but humans have attention, so they try to focus on the most important things first.
Not necessarily, actually. The approaches are often pick up the objects in the picture and analyze each object rather than analyze the picture. And they do this as two independent steps.
Maybe.
But yeah, so it's quite interesting because for human, probably I agree, it's easier to detect simple objects. For computer, opposite. Why? Because we have edges or differences of colors, and for model, it's all features. And if you have more features that represent this type of objects, of course, it's easier for us to detect these objects. Not just like if you take like naive bias, probabilistic, it's easier for us if we have more data representatives to be more precise as compared to some round stuff like apple. It doesn't have anything, can be also ball, also can be whatever we do, right? If you just consider it, if you consider color, then I will say, okay, we have 7 airlines playing an apple. So if you just consider colors, not really different. It's just colors, it's just color histogram. So point is, actually complicated objects easier to detect than the more detailed one, than the simple objects, just like this. And one of features, as I just said, can be color histogram, right? Or intensity histogram. So it's basically very easy. We just calculate pixels of a certain intensity in, and then we just combine all of them in the bits. So, for example, we have 256 colors. We divide the 256 colors into bins, whatever number of bins we want. And then we count and we get the histogram. So this histogram represents the image in point of view of color. And what is interesting, I'm not sure how exactly it works in Google or other image retrieval search engines, but it's very interesting. And if you take a picture of something with a very representative color, post it in Google and try to and ask him to find, he very likely will find something just with similar color. You take a chair or like a boot, he will find a crocodile, with a green crocodile, green chair. It's very easy. Google is very good on finding things that they already have indexed in their database, but if you start making a picture of something new for Google, Google become not good. Yeah, briefly say that. So current image retrieval systems are actually not so good as is expected to be. So color histogram, or sorry, intensity histogram will look something like this. You have some picture. It's gradations of gray, right? Different levels of gray, and you put it in histogram, just like in MATLAB, and you get something like this. So that's quite a nice representation, and very often it's enough, because again it's very fast. Why we need to do something much more complicated? We can do just this, and it's already enough. So, roughly speaking, it will be something like this. I don't think I need to really explain how to draw histogram from the data. Just briefly, we have bins, for example, 8 bins. We have the images. Images have gradations of color from 1 to 8, and we count each of them and draw the histogram. And of course, each bin can be more than one color. For example, 1 to 3, 3 to 6, and so on.
How are different colors represented? Pixel is not one number.
Yeah, so we'll compute 3 histograms, and then we can see all combinations for level intensity. For example, we get 4 intensities from one color, then 4 bins for one color. Then bins will be 1, 2, 3, 0, 1, 2, 3. Then you'll get another 4 bins for another color, then another 4 bins for another color, right? And compute intensities of each color. And then we see all combination of all bins. So you'll get how big a histogram will be if you have 4, 4, 4. It will be histogram of size 64, right? Because it will be all combination of bins. Another way, just put bins together. That's another. It will not be exactly histogram, but it's a way which is okay because it will be featured for us. So, and we have another example. We have this parrot, and this is a histogram of this parrot. So, and we have this. Is it easy image or complicated image? How do you say?
Complicated.
So, how histogram will look like?
Strange.
Maybe the same.
Somehow.
It will be, good similar to that one.
You will have many peaks or
Yeah, I suppose we will have this, but if we see the people on the background which are far away from the front row of the picture, so there will be almost no peaks.
it will look like this.
Uh,
And
there are some things, yeah.
yeah, correct. And actually, in terms of color, it's quite difficult to say what is inside. We need to have some more complicated analysis. As some research in image retrieval, they say they can analyze the food. They can have a picture of food, they analyze what food is this, and then extract the calorie level of food. And based on this, they can say a person who takes this picture, what is his average calorie intake. But, I mean, sorry, if a person take a picture like of a market, Chinese market or whatever market, where there's a lot of people, a lot of apples and everything, and or take a picture of some food which includes many ingredients, many components, then it's very difficult to understand. So I would caution these people who will do that. Yeah, who knows, maybe in future we can do it by percent. By now it's not so good. And how about this one? Is it easy or complicated?
Easy. 100.
This is histogram. Very nice, right? It's just like awesome. But in terms of colors, it looks similar to blue and to apple as well. So no, it's always questionable, right? From one point of view, we say this image is complicated, but at least it has some representatives of color, because this one just have one peak. It can be like everything with black and white stuff. So which image do you like the most? Which one is the best one? First, second, so.
Moon. The moon is the best.
Okay. In terms of color representation, actually not, because
It's very simple.
no, because it's just like one peak,
Yes.
and it will produce anything like this. So our question is how can we improve it? Now we have color histograms, right? Like this. How to improve it? Now you have just the distribution of colors. So what we can do to make it more related to objects in a picture. No ideas.
Maybe we need some filters
Filters.
to eliminate noise or maybe area we need minimize the area of searching.
Okay, think about it. I'll go back to it later. that's somehow relevant. So basically, what we do, we quantize the image into the bins, and then each pixel is denoted by bin, but not by actual color already, right? So what we do, we extract color value for each and quantize it out of M quantization levels. And M can be arbitrary. It also depends on task, so it's how big feature vector you want to have. And then you collect the frequencies of color for quantization level, which in corresponds to a color of quantization level. That's how we build the histogram. So this is regarding the question when you have three different levels. Yeah, we either just append them or compute all combinations, so we'll have multi-color representation. For RGB, for YCRCB, it's similar. We have three different components as well. We get different histograms of each component: component of luminance, component of chrominance, component of colorness. We come up with something like this. Very powerful feature, actually. Only histogram can help us a lot in many cases. Except histogram, we can compute something called color moments, which in fact is just mean and variance and other statistics like this. So for image, we'll have only two values. It could be useful as well to represent the general level of image, how color quality is or so. And we also can do it for subregions of image, right? We can move the window and compute it in every small window in the image. So finally we get the subregions. So, but there is a problem with histogram. We can see two images. Is this similar? Or there's it's actually similar images, right? But far away you see this lady, she looks like a dog sometimes. Color-wise she looks like a dog. But
Otherwise they are, yes, it's this.
yeah, can also not like.
The colors are just the same.
Correct. Yeah, I guess this image is also a bit preprocessed to make it.
Yeah, yeah, so this is quite a real situation, but for humans I should agree that the face of woman is recognized faster and more accurately than.
So if you will see the dog, which will be a size of a lady and walking on legs. Maybe confusing.
First what will happen, it will be cognitive dissonance. So if we face some unusual situation or unusual information, so first of all we are confused, then we try to understand and to process how this information could happen, could come into our life, and what should we do with it. So first maybe first impression would be that this is a costume or something like that. The first thing.
I guess we need people like you in our research group.
That's
very important.
That's why I'm in plastic.
Yeah, it's actually very important to understand this moment, because every representation initially must be based on some source, some observation, and we can assume something represents.
I can send you the names of authors, the psychologists who make research in, for example, objects detection or something like this. These are mostly they are the research of 70s, but they are still actual.
It's very often can be applicable.
Yeah, of course.
So go back to our question, right? So what else we can add to here to actually make it different? So it's actually quite easy. We can have two histograms. One histogram will be related to color, right? And another dimension will represent actual the position of the elements in the picture. So it's called the CCV representation. In fact, the abbreviation is color coherence vector. So we will analyze not just the pixel itself, but also its neighbors. So by doing this, we actually can extract the regions of a certain color, right? So it's more close to objects. So we will get such a matrix, which our image, it's already bins, right? So it's already bins representation, right? So here I guess we have 4 bins, or maybe 3, probably 4, 0, 1, 2, 3, right? And we will get something like this. You see, by color, we show the different regions of the same color, right? So we have red region and blue region. You see pixels that are adjacent in diagonal also called adjacent. So this 3 blue is called is a group, and so on, right? Black region, greenish region, and 3 region region with a gold color, right? In the middle with a third bin. That one is just only one, so it's so-called rare component, right? And then we will do something like this. We divide it by regions, and then we will get such a matrix, where HA will be those regions where we have big regions, you would say. Those pixels too that belong to big regions, big groups of pixels. And the second one will be those ones who belong to small group of regions, small group of pixels. So for example, you can see for bin 1, right? We have 11. So one of them is this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? This one big one. But we have another small region, which is 3, which is blue. So we'll say that for color 1, for bin 1, we have 11 big regions and 3 small regions. For color 2, we can see that we have only 1 big region. We are adjusting, right, diagonal adjusting, and we don't have small region, 0. And for color 3, we can see 6 and 1, right? This is clear, right? This is very easy.
There will be more than 2 regions which come up.
Yeah, if you find the big, yeah, we'll just have a threshold which considered small, which considered big, and then we'll just.
There will be more rows in the second table.
No, that's always true.
We always take the biggest and smallest.
Sum up, yeah. We'll just sum up. So idea here is just come up with one more histogram that help us to say how many adjusted regions and how many individual pixels do we have. Of course, this one is a toy example, right? So we can get something much bigger, much nicer for your images. And we treat them separately. And actually, we say that for us, the big regions are more important because they are related to objects. It's true, right? The big regions of same color, actually not same color, same bin, right? Which is similar color, are logically related to objects. While all others will be some small elements of background or whatever. Right? So we will have this mu, right? This mu will be actually bigger for images with similar QADA, with a similar alpha as compared to similar beta. So we will prioritize the similarity in the big objects into images as compared to the small regions. Okay? So it will work like this. What else we can do? We can use a texture. Texture is something that repeats with a certain. It always repeats, right? So textures look like this. So basically, flowers also a texture. So it's like a certain pattern that often repeats. And if we can extract such a pattern from an image, it's also quite a useful feature because we can extract some texture. It's like texture can be a surface of some element of an image. For example, like a carbon car, or whatever. It can be a picture. Or, for example, it can be flowers, right, or something like greenery behind. So if we can find this texture, and then we can extract it, and then find another image, we can detect something like outdoor events or something like this, right? So it's important. So, and there's another thing. This from sociologist and psychologist Tamura representation. This one I don't go deep to detail, but the point here is there are a lot of social scientists and psychologists. They also work on colors, and they come up with some properties that are related to human perception of colors, human perception of the images. So they have categories like coarseness, contrast, directionality, regularity, roughness, and you can come up with some heuristics. In fact, there are some algorithms can compute all these features for the image, and after that, you can leverage it and use it as feature for your further work, right? And now we come to edges. Okay, let me think. Did I say? I didn't say. Okay, there's such a thing. There's a simple version, but it's still yet quite popular. Is a Sobel operator. This 3x3 matrix has variations for 3D space and so on that you can apply with shifting, like a Windows shift to an image, and by doing this, it will be actually an approximation of the gradient. You know what is gradient, right? So gradient basically gives us the direction of growth of the intensity of this representation of image, like of intensity of grid, for example, in a certain place. And we also can get the magnitude of the gradient by taking the norm of the result matrix. So to norm. So it's very nice, right? So we have in every position, every window, we have gradient and we have a magnitude. So what edges will be in terms of gradient and magnitude?
Oh.
In terms of magnitude.
Mm.
Edges will be a big change of intensity, right? But for example, for this girl, you see, we have background and we have white pants. I guess it's like generated. Yeah, whatever, doesn't matter. We have white pants and we have background. So intensity of white, cannot say intensity of white, but okay, intensity of green. You see grass behind, right? We will go there and then immediately green become not intense. So we will get direction like this. In fact, it's in X and in Y. We'll go this direction, and we also get the change, the magnitude of change. So every time when it changes a lot, it means it's edge. It means there's something changed in the picture. Very easy, right? So when we can come up with something like this, which called the edge histogram, where we have beams for each direction, which is our tangents of the two observable operators. And we also have a magnitude, so we can just split it into beams, for example, eight different directions. And also can split beams into magnitudes. And then we can build a histogram, which will represent our image in terms of edges and in terms of magnitude. And further, of course, you can even apply the previous techniques, which is CCV, to consider the spatial aspect. Where is it? Where is this object in the image? Then it will be just awesome because you can do everything. You can detect edges and you can consider where these edges happen, so you can just detect objects, right? In fact, in the future, I'll talk about one more thing. This is also leverage on this edge information. And this edge histogram is a very powerful feature as well. So we have two. We have colors and we have edges. So also we can represent it in a segments, right? We can compute it for each segment of image, not for whole segment, not for whole image. So if we can compute it for every segment, then we also kind of consider the spatial information, right? So compared to other images, if the same segment have a similar histogram, then we may say that these similar objects, similar images. So just like here, right? We have object of flower. We need to detect it in the center. So that's exactly what we do here. But of course, it becomes more expensive because we have to do everything many times as we can. So one more thing we can have is a very easy feature. Many of the images have some information actually written inside the header of the image, just like location and type of camera and so on, so on, so on. And this is actually very useful for us because this is data you can just see like in Windows Explorer, right? You have a lot of interesting stuff, and all of this thing can be features. You can even know about location of image, and we can even evaluate roughly income of person who would shoot it. At least for those expensive cameras. Or occupation, maybe as a photographer. Yeah, maybe now it's not so easy. Before it was more difficult to have a nice camera, a nice microphone. Whatever, that's a direction I should think about. It's useful features to use it. So, and and sometimes you have GPS tracks in some cameras. So for XC format, right? And it knows the conditions of all the picture. And it can be related to calendar, so we can date. So what advanced representations of image we can have? We now have the edges, we have the colors, but we face a problem if we have the same scene in different scale or in different or in a different angle, then there's no way for us to detect, at least in terms of edges. Why? Just because edges are related to position, how we convert, because we're against this, right? So to detect it, we need to rotate the picture first, and then we can do our edges. So that's why researchers come up with something called SIFT. How many of you know what is SIFT? Okay, you're from. So you know about small
Little
SIFT.
bit. Not small stick, a little bit of sift.
Okay, so the SIFT is actually quite complicated thing, so I won't go too much in detail, but point of SIFT, okay, most properties of SIFT, that is scale and rotation invariant. So it's widely used in like logo detection, for example. If you have some logo of car, you need to detect this logo in cars in a highway, or when you need to find some logo in product, and product can be flipped and rotated in any way. So we take a square windows around the interest point, and before that we detect interest points. Interest points is kind of candidates of having something representative about this image. To get interest points, we first can do the previous operator just to take edges. It's already fair enough to find the interest points. Another way how we can do it, we can build so-called Gaussian pyramid. When we apply Gaussian filter many times in image, and we see the adjusted levels of pyramid, and we basically say in which level some edge disappear. And so there will be something that won't disappear, and there will be something that will disappear. So that one won't disappear as interest points for us. Basically, kind of strong image representation, strong image features. That's why we need complicated images, because we have more interest points, and we can. And we will come up something like this angle histogram, as I explained before, just like basically different beams of angles, right? Because we cannot walk with this exact angle. It may look like this. I don't think, can you see too much here, but all these circles are actually interesting points. Blue circles is a gradient bigger than 0. Red points is a gradient smaller than 0. Actually, both of those are more important for us. We care both because all of them are representative. So we get something like this, and then we divide this 16 window into 4 to 4 grids. I'll show here 2 and 2, but it doesn't matter, 4 to 4. And then we build the angle histogram of each of the grids, and then finally we will get 128 dimension descriptor. Correct? And this will be SIFT. So it's basically descriptor. So we take interest points and take pixels around this interest point, big enough, and divide it into subregions. And for each subregions, we detect the angle histogram. And angles are taken from the so it's a gradient angles. Just angles of growth. And then we can match images like this. We have the same book, and this is the book. Yeah, we have something same in mass and also independently, and we can match the strong features of points of interest to each other. So we can do retrieval of something in messy pictures. And as far as I know, what was the initial task of the guy who proposed the SIFT. He was aiming to find something find something he has in the pictures. So it's kind of image queries into a picture. But SIFT descriptors we have a lot of SIFT descriptors usually. So the dimension is too big unless we have a lot of data to process, so the dimension will be too big. So we need to come up with something to group them together to come up with something called visual words. And we will adopt the bubble words model again. It means we don't care the sequence of shift features, the relations, the sequence relation between them, we just care that itself. And it's just the same as information retrieval, but we treat every shift features of as a low level kind of letter. We will say it's a letter because letter form of words. So we have an image, and we need to come up with some backup words from this image. And words from this image will be, roughly speaking, some interesting segments of this image. And we don't care the order, right? You can organize it. So the whole idea is a quantized shift again to certain bins or clusters that will represent our visual words. So it will be basically groups of representations of interest points in the image. So it's one more level of abstraction. So we have these regions, and all of them come up to some points, and then we cluster these points, and these points will be words for us. Clear or need clarification? Yeah. So after that, it will work like this. We use hierarchy of k-means. All of you know what is k-means, right? Yeah. Okay. So k-means is we basically pick up some centroid point randomly and look for all points that is around this centroid, and then we subdivide again, find new centroids inside one cluster, and so on, till finally we will come up with something that will allow us to stop cluster, right, for certain region. No, for example, for this cluster, which cluster? For example, for that cluster in the left corner, we will see that actually all points are nearby to center. And it will mean for us, okay, it's no need to divide them again because it looks like this is a cluster already. So probably it will be some interesting word inside the picture. Okay, we're done. Then we will come up with some tree. And we can traverse this tree in logarithmic time, so it's quite fast. And we have visual words, which will be a list of this tree. And usually words will look like this because it's gradients, right? So we can find what it looks like. So each image will be represented as a histogram of visual words. And visual words will be cluster of shift features. And shift features will be a means of gradient directions, which will be extracted from interest points, which are probably edges or something like this. Okay, so I hope everybody get the idea. So we will have such a representation of each image, and it's just awesome because we can detect objects like this, and to the concepts that an image is like more high level, right? We'll talk about concepts a little bit later. So, for example, in this image, which concepts do you see? This is a Singapore park. This is the Universal Studio Park in Singapore. This is the main symbol. So which concepts in this picture do you see? Concepts is some high-level objects, I would say.
People.
Grass.
People. Again? Grass.
Crowd.
Crowd. Crowd is not a concept, I guess.
Group of people.
Crowd is a many
Photo
people
camera.
concept. Many person concept. Again?
Camera.
Camera. Where's camera?
One might have.
No, I mean, you're all correct actually, right? As example, we can detect trees here, for example, right? So, something general is, for example, a tree. We can find in many pictures, so we can train a model. Or we can detect this guy as a landmark, just in case if we will have enough images of him from other points, then we can detect him. If we don't have, then I don't know what's that. In fact, it's a funny thing. It's a symbol of Singapore. It's a lion with a tail of a mermaid. Yeah.
Like a
But
fish?
it looks like a shrimp. So, yeah. Because they call it Lion City because when they found Singapore, they actually see the lion on a hill. Yeah, and then they combine mermaid and lion to become this. So, and it also can be other things that you just mentioned. Can be sky, can be people. People is not a concept. Person is a concept probably. And you have stairs, and you have statue, right? Because that's actually difficult to detect because every statue has different shape. So how I know this is statue and not anything else. And actually that one also statue. And these concepts can be 10 to 30,000, these basic concepts. There's a dictionary called ImageNet. It's a hierarchy of different categories of words. So this, WordNet, I'm talking about WordNet. It's a hierarchy of different categories of words. It's like a huge hierarchy, you can traverse it. So there's guys who found the pictures for many of these categories of words, and they found a lot of pictures for each category, and then come up with around 1,000 categories about which they have a lot of pictures. Not just like, I don't know, just like pants or shoe or school, right? They come up with a lot of pictures for this category. It means this category is easy for us to detect because we can represent them as sieve, color histogram, and so on, all these types of features, and then we can just find the nearest neighbor based on cosine similarity or gradient distance or other type of distance, right? Like Chebyshev, for example, a nice distance will work very well sometimes when you consider only one, the most strongest feature. Yeah, and we can actually detect these categories. So, and there is challenges that happen every year when they try to recognize these concepts. They train on the existing ImageNet data set, and they try to test, they try to recognize this concept. Of course, they don't recognize Merlion, but the task looks like this. You see Merlion in many different positions. But you still need to recognize him, right? So now you know how image can be represented. So you'll see, okay, probably background is very different, color is kind of represented. So why not I use color histogram and edges, for example, right? So it should be fair enough to try to detect from these features. Yeah. So yeah, and then the test will be something like this, and you need to understand that this guy is. That guy is actually the same thing. And they have 1,000 categories, and they have test pictures to you, and you detect, you retrieve concepts for this picture. And in fact, many pictures, many concepts can be in one picture, right? So it's kind of image retrieval competition. They do it every year based on ImageNet. And recently, Google came up with a deep learning architecture called GoogleNet, which is now implemented as part of Cafe framework. And it's very powerful for these 1,000 concepts. So if somebody decides to work with images, I would suggest just try to run this GoogleNet, which is already packed everything, you don't need to do it too much. And see how many concepts from ImageNet, from 1,000 concepts you have in your image. And maybe it happens that it will be very representative feature vector of 1,000 concepts. And maybe you don't need too much, and you'll have already a very nice representation of images. That's how we do in our work. So. And yeah, we have, of course, other images that is not related, so to understand it. So the overall pipeline could look like this. We learn on images of bicycles and images of, what is this? Oh, and images of heads, yeah, pictures, yeah, probably heads. And then we train for every binary category, we train a classifier, right? I mean, for those who are not familiar with machine learning, it's just some black box can input feature vector, output some label, right? I guess all of you knows what is like regression, linear regression, just like to feed data or something. So we can, if we have 1,000 concepts, we can train 1,000 classifiers like this, and each of them will output the result and also probability that this image belongs to this concept. And you'll get distribution, right? Not exactly distribution because probabilities will not sum up to 1, but you will get the levels. You will get the levels. Actually, you can get distribution just divide by 1,000, right? But whatever, you will get the levels. The distribution of image belong to some concept. So it will be the vector of features. If you have many images for some guy, you sum up all of these vectors and you will get the distribution of some user among all these 1,000 concepts. So it will give you a feeling what type of object this user generally posts, which is very nice. It's already very high level representation, right? It can be used for classification, for image retrieval, and so on. And the model can be either discriminative or additive. I mean, this is basically different ways to train that. We can randomly select some sample of negative samples for our classifier. So this one would be we want to do zebra, right? To be positive sample, and we also get other images that are not related to zebra. We can smartly sample it from all other concepts images. Train our classifier just to detect zebra. So it will output zebra or not zebra, and it will do for all other, and then we get the probability of zebra for this certain thing. In fact, for us it doesn't really matter. Will it be zebra or something similar to zebra in our images? Just because for us, our aim is not to detect zebras. Our aim is to have some nice high-level representation of user. Just like example in our recent work, we found that the big concept, parik, is BIG, is very similar to, very popular among female users. Why? Because they take a lot of selfies and they all have hair, right? So we detect hair. And we found, okay, female users are really popular with the big concept. So it's a very powerful thing. So why not we combine everything together? We'll get sift, location, some statistics about image. We will get color histogram, and CCV features, and edges. Combine everything together and train our classifiers. Then we can be, that will be quite nice representation. Another approach how people do now is just come up with some deep learning architecture with some neural network. That you feed in image inside, then it do something nobody can explain what it does. And then it outputs you something. And this something works very well to predict your label. And nobody knows what is this something, and nobody, it's hard to, especially mathematically, explain how neural networks really work because it's very nonlinear models. Yeah, and I guess there is a tutorial, right? With linear and neural, so I shouldn't advertise other tutorial, otherwise you will go watch the tutorial. Anyway, so this is a separate topic, so if you're curious you can read or just. And we have locations, right? I'll go quite fast for location because it's already, I'm late again, the thing, right? We have this all location-based services, and one of them, main of them is Foursquare. And this is video. You can pick up it from slides, YouTube videos where they say how people perform check-ins over time in different regions in the world. So it's very interesting to see. The different places will shine, one will shine more, one should shine less. Some will light in the morning, in the evening, so just very interesting visualization. This is the real thing you can go through. In fact, what kind of location features we use? Now we need to leverage on different aspects of check-ins users. We have social aspect, which is social graph. I was talking about it before a little bit, so. But anyway, it's just like social graph, so we can build social graph and do some analytics of graph, detect communities and so on. We have temporal aspect, which is important because sequence of check-ins The temporal sequence of check-ins for one people may differ from another people. How fast they check in, how far they travel in the city, right? It's called mobility. The third one is mobility, which is related to temporal and geo-aspect. It's all four forms of mobility, and geo-aspect is just movement in space, right? So we need to consider all these three aspects to do the feature engineering for this stuff. And you can see this in this screenshot from Foursquare page. You can see the geo-aspect is actually text markers in the map, and you have friends feed, which is social aspect, not so developed in Foursquare actually. We found that social aspect not so useful for Foursquare. And we have this ads of friends, and we also have some venue recommendations that Foursquare recommends to you when you to go. And activities you can perform with Foursquare is like this. You can perform some check-in, and you can see some recent check-ins around that place from your friends, and we also can get some recommendation of places around it, just for me to do. So this is the types of features can be extracted from Foursquare. This is features from work by Nolas. He's from Cambridge University. They work heavily on mobility. These features are very related to movement and to temporal aspect. So some user-specific features can be some history of visits or some friends check-ins and some preferred venue types. Right? At the same time, we have the geographic movement of a user. Right? For example, how much this user moves from one type of venue to another type of venue, and also go to synagogue, yes, yeah, and so on. So it's basically describes how active user is. And here it's actually very important. We need to consider the density of the region. That's because in US people may travel to shop for 20 kilometers from their farm. In Singapore, everybody will travel just a little bit till nearest shop. Those are exactly the same thing, right? So we need to know the density of the region first, and then can be not like real physical distance, but more about how many interesting concurrent places before place you go, and your current place and place you go. It will more represent how much effort you spend to go there as compared to just like pure geographical location. Yeah? Also some temporal features, some trending places and trending place types. So trending means some places are heavily associated with certain time. And another one is a place network, because places actually explicitly connected to each other by referring one place to another and by building the places of the same type. And also implicitly by co-occurrence of the check-ins or visits of certain place type. And they found that, yeah, in this work, the occurrence is quite nice work and very simple to do, so you can read. And all slides are available there, so it should be fine. So there are different types of features, right? For example, you can see that historical visits of user is not very stable feature because it changes from in a different big days. You can see that the performance of the approach is changes, and the patterns is changes during the temporal aspect. Other features are quite stable, like place popularity, category preference, physical distance, run distance. Run distance is what I was talking about, the distance, considering the density of the region, and activity transition, and hour of a day where you go, and day actually, and category of day, week and weekday, and category of hour, peak hour or non-peak hour. So these are features they come up with, and the task was just predict the next place where a person will go. All these mobility features are very important. But we shouldn't forget that besides mobility features, we also have so-called venue semantics, which is very related to person's interests. It's types of places we go to, right? And we have Foursquare venue category that looks like this. So we have different categories of venues like restaurant, cinema, gay club. They even have this, and they have prison, so it's very fine grains, it's very nice. So we can cover all interests of user, and it's nice for us because we can learn a lot about users, right? Further, we will have these metrics, and we can see anything, but basically the feature metrics will be distribution of user among menu categories. So you'll get some user who visit restaurant 2 times and visit airport 3 times, and all others will be 0. So we divide this one by, okay, it's almost 3 times. So we divide this one by 5, this one by 5. So we get the distribution of this user for this user among different categories. Here was one and 2, but doesn't matter. So we'll see which places this person likes, which places this person tends to go. So, and another thing what we can do is apply LDA on it. So what will be words for LDA here? Places. Not really places.
Categories.
Check-ins, actually check-ins. Yeah, and it will be exactly not places, it will be category, because there's so many places in every city. So it doesn't really make sense. It will not likely to appear often in our small data sets. So we'll use categories. So we can come up with these categories. You'll get this LDA distribution. It's also very powerful. You can get something like this. For one user will be, if you have a six topics, one user will be food lover, and another user will be professional, and one more user will be, what is this, like shopper, right? And why we say shopper, food lover, students, teenagers, professionals? By going through the words categories that topic is represented. So we see that the first topic is Malay restaurant, mall, university. So we can see that it's a lot of food-related stuff there. We just say, okay, this one will be food lovers. So basically in LDA we have the distribution of topics among words, so we always can annotate with some name if it's possible. Sometimes topics doesn't make sense, so we need to find another approach how to model it. And finally we summarize. Sorry for too long. So we have many types of features. Color, histograms, CSV vectors, textures, edges, visual words, concepts, meta information. And you have this location semantics for location features. And we also have different mobility-based features, which is based on mobility, the distances, how person travel, and so on. And we can even apply LTO on it, so we can have a lot of wide range of technologies we can use to do features extraction from our location image data. So if you have images and location and you want to try at least big part of this, and you may lose something as well, just because. Also, I suggest try deep learning because it really works well. Nobody explained how it works well, but it works really well.
It explains. It's so relevant Wednesdays.
Yeah. In Wednesday?
Morning.
A little bit deep learning tutorial, right? Yeah, hopefully they will explain, yeah. My model will do tomorrow, so it will be very well equipped for Thursday when you're supposed to show the project. So, may I know who gonna participate in the project setup? I still don't know if it's grading or not, but we need to divide by groups. Yeah, this one was introduction to classification, so in the next lecture. We need to predict features, predict labels. Doesn't matter which labels, I just go through the classification. So we have our data set. I described it after the first lecture. And I encourage everybody to try to work on it before Thursday. So can we split on groups? For those one who gonna keep working in this model? Or it really doesn't work here? Okay, so can we decide in this way? you will take the slides and you will maybe take a picture of this today. And you will go to the web page of the data set, maybe go through the paper and study what is the data set is and what type of feature are there. Maybe download these features and try to do something with these features. Just try to understand what is this. By tomorrow I will ask organizers, are they going to grade you or not? If they're going to grade you, for sure you have to present. If they're not going to grade you, then for sure you still need to present. I hope. And so the description of data set in the paper, right? And you can also write to my email address. I'm actually here and I will respond about any questions. I actually want you to be engaged in this process because without trying this, you will not really feel how cool field we have and how nice to do some interesting insights in data. So, and we can use anything we want for this. And all slides will be available here. So basically, I think just last moment. Basically, the oh, we have somebody. It's probably after we show the Twitter thing, keep playing videos from the recommendation. Yeah, it's nice that this video is not too compromising. Yeah, so we basically have this data set and we have three cities, New York, Singapore, and London. And you have multiple types of data. You have three types of textual features, one type of image features, which is image concepts, and one type of location features, which is distribution of Foursquare categories. So can we try to do till Thursday, till the last day? Because they put the Wednesday in the between just to give you some time to try to do this. And in fact, the Thursday, the first hour of Thursday is planned to be spent on this kind of features. So can we try till Thursday apply any machine learning technology to detect all these 5 labels for 3 cities and get some report? I actually hope at least those one who are friends can form some small groups and try to tackle this task. Can you try? Because this was another guy there also from McLeod. They also going to do this, and I think you will do this, right? So because we have a lot of time. Yes, and these 2 guys in bags, they're also very cheerful, so I think they can do it, right? So let's make our last day fun, and our professor, the leader of our lab, he will come in the last day to give the last lecture. So it will be a nice chance to discuss with somebody who is really leading in this area and also maybe get some opportunities. Because in our lab we actually hire interns and engineers now. It's one of purpose of his and my visit to here. So we hope to get interest in this area of people and we hope to get more people in our project. Okay?
So do you have the data set at hand? Do you have the data set at hand?
The data set is on the web page.
No pre-downloaded, so that we can try to play with it right now.
Yes, of course. It's on the web page. It's actually available for everybody, but
Well, the local internet is probably not as fast as simply copying to the local.
no problem is I don't have it with me, but I think it's very easy to upload it. For tomorrow I can upload for myself and copy to everybody.
What's the size?
It's hundreds of megabytes. It's yeah, it's not big. It's actually not big because we don't include any real images. We do features already. Right? It's like around 0 megabytes. It should show them. Yeah, so this is a link to the data set.
Excuse me, I'm terribly sorry, but the next talk will start in 5 minutes here, so I guess, because, so maybe we can finish it now or break.